This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is DC voltage sources in parallel circuits. Our objective is to examine electrical properties of circuits, including parallel configurations of multiple DC voltage sources. We'll examine battery bank characteristics and take a quick look at a DC power supply that allows parallel configurations. As you are no doubt aware, voltage across elements in parallel is the same. Voltage is a two-point measurement. This simple fact explains the fundamental rule regarding multiple voltage sources in a parallel configuration. The rule being this: multiple voltage sources must be of the same magnitude and same polarity when placed in parallel. Allow me to demonstrate. Consider a 12-volt battery, limited to supplying a maximum of, let's say, 2 amps of current, supplying power to a 12-volt rated DC motor that draws 1.5 amps. This is totally fine. However, let's say you wanted to run another identical motor off the same power supply. An additional 12-volt rated DC motor will draw an additional 1.5 amps of current. As a result, the battery bank needs to supply 1.5 amps plus 1.5 amps, or 3 amps. 1 amp in excess of the permitted 2 amp maximum. This is not an ideal situation, and this might damage the battery. A simple solution to this problem is to connect another identically rated 12-volt battery in parallel to the first, such that their polarities match, positive to positive, negative to negative. This collection of batteries is sometimes known as a battery bank. Key to understanding the rationale behind this approach is Kirchhoff's current law. While voltage remains the same, a parallel relationship of two similarly rated batteries can now provide twice as much current. Given each battery establishes a 12-volt differential with the same polarity, the 12-volt rated electrical loads still experience 12 volts. However, each battery can now share the responsibility of sourcing a portion of the required electrical load. Assuming equality, both batteries provide 1.5 amps each for a total of 3 amps. Thus, each battery is tasked with a more manageable current draw below the permitted maximum of 2 amps each. Beyond sharing the resultant load current, parallel arrangements of multiple batteries result in increased energy storage capacity. We'll examine the details of batteries, including discharge characteristics and charging methods in later lectures. However, let's use this simplification. Consider each battery as a finite reservoir of a given amount of energy. Let's say each battery contains 0.48 kilowatt hours of energy, or more appropriately, 480 watt hours. Given two identical batteries, this represents 480 plus 480, or 960 watt hours of energy, just shy of 1 full kilowatt hour of energy. If each battery draws 1.5 amps, an application of the power formula demonstrates that each DC motor necessitates the consumption of 18 watts of power. 2 motors means that the battery bank needs to supply 36 watts of power. My question to you is this: how long can the battery bank containing 960 watt hours of energy do so? You'll recall that energy is power times time. An algebraic rearrangement of this formula suggests that time is energy over power. Substituting our given values demonstrates that the battery bank can power these two loads for 27.6 hours, just a little bit more than 1 full day. This being said, after a full day use, i.e. 24 hours of continuously supplying 36 watts, results in the expenditure of 864 watt hours of energy of the available 960 watt hours, bringing the batteries down to a 90% depth of discharge. Such a high depth of discharge would considerably shorten the lifespan of these batteries if this occurred on a regular basis. Let's say we wanted to provide a more reasonable depth of discharge to ensure the longevity of the batteries and, in an emergency, provide at least 2 full days of autonomy for the system. Autonomy, by the way, is a measure of how long a battery bank can supply power to an electrical load without a charge. If 2 batteries in parallel can provide slightly more than 1 full day of autonomy to the system, it stands to conjecture that 4 batteries in parallel can provide slightly more than 2 full days of autonomy to the same system. This larger battery bank now contains 4 times 480 watt hours, or roughly 1.9 kilowatt hours of energy. As previously, a full day of use, i.e. 24 hours of continuously supplying 36 watts of power, results in the expenditure of 864 watt hours of energy of the available 1,920 watt hours, brings these batteries to a more reasonable 45% depth of discharge, considerably lengthening the lifespan of these batteries. You'll additionally note that 4 batteries in parallel further divides the current demanded from each battery such that each battery is tasked with a smaller 0.75 amps, or more appropriately 750 milliampere task, such that the two electrical loads consume 4 times 750 milliamperes, or 3 amps. Long story short, voltage sources in parallel increase the energy capacity of a system, and the current demanded by the system is ideally equally proportioned between each source. Let's now discuss violations of the fundamental rule of elements in parallel, this egregious violation being the parallel connection of sources with different magnitudes. Consider a freshly charged nominal 12-volt battery, presently at 12.6 volts, connected in parallel to a deeply discharged nominal 12-volt battery, presently at 10 volts. This is a bad idea under full sail, because with no current controlling element in between the two sources, consider the 2.6 volt differential across and the current through the theoretically 0 ohm wire linking the two batteries. Ohm's law demonstrates that a massive, theoretically infinite surge of current would occur between the two batteries, such that the freshly charged battery discharged into the deeply discharged battery in an uncontrollable, potentially dangerous manner. A common method of preventing this from happening is the incorporation of a semiconductor device known as a diode in series with each battery in the battery bank. We'll examine diodes in greater detail in later lectures, but for now, you can think of them as the electrical equivalent of a check valve, which is a device that permits current flow in one direction only. The arrow indicated on the diode schematic symbol indicates the direction of free flow, whereas the wall indicates the direction of no flow. Configured in this fashion, each battery in the battery bank is permitted only outgoing flow and will not allow incoming flow. This would prevent the fresh battery from discharging to the deeply discharged battery in an uncontrolled fashion.